Performance studies of gap-graded mixes using Elastomer Modifier for wearing course. Abstract road construction crossing the world created huge demand for construction materials. Natural aggregates is the prime material for the road construction. Use of aggregates leads to question about the preservation of natural resource. In other hand, use of recycled pavement asphalt, RAP, as an alternative material in place natural aggregate which makes environmental friendly construction material. This research investigated the feasibility of using reclaimed asphalt pavement in stone mastic asphalt mix by modifying the binder with waste engine oil and Elastomer Modifier. RAP is replaced with aggregates at 10%, 20%, 30% and 40%. Further, in order to increase the percentage of RAP in SMA mix, waste engine oil and Elastomer Modifier is added, i.e., RAP of 50%, 60% and 70%. The results indicated that 30% of RAP is found to be feasible through laboratory investigation for SMA mixes and 60% RAP is found to be feasible to use in SMA mix through laboratory investigation by modifying binder with waste engine oil and Elastomer Modifier. Keywords: stone matrix asphalt, wearing course, reclaimed asphalt pavement, Elastomer Modifier, fatigue. 1. Introduction. 1.1 Stone matrix asphalt. India, which has an ideal vision for growth and development of infrastructure. Infrastructure development is a core aspect of connectivity which connects different places through different modes of transportation, wherein road connectivity is undoubtedly one of the most important mode. For a robust road connectivity network, the study of pavement structure and their durability and resistance will be crucial aspect. This makes us look at some of the key aspects like type of pavements and materials used for construction and the cost incurred to lay the pavement. The pavements undergo repetitive loads and the number of deflections and numerous loads are imposed once a wheel moves on the surface where the load is dissipated to the underlying layers of the pavement are subjected to diverse type of distress. The major distresses found in flexible pavements across the globe are rutting and fatigue. Stone matrix asphalt is found be an effective alternative on heavy traffic pavements due to its stone-on-stone contact. It provides resistance to rutting and higher binder content increases fatigue life and reduces reflection cracking. 1.2 Reclaimed asphalt pavement. Reclaimed asphalt pavement are the materials derived from reprocessed pavement which contains asphalt and aggregates. The derived materials are subjected to crushing and screening to obtain RAP of well-graded aggregates coated with bitumen. Recycling of existing asphalt pavements allows the industry to produce new pavements with effective utilization of material and energy, making it cost-effective. 7. For this study, RAP is procured from Chittoor district where some part of Bengaluru-Tirupati highway, NH206, was scarified for construction of cement concrete pavement. 1.3 Stabilizing additive. SMA is a gap-graded mix, contains high percentage of voids due to which the bitumen content is more. Hence, the stabilizing additive should be added to the mix to reduce the drain-down characteristic of the mix. 3. In this study cellulose fiber is used as stabilizing additive. 1.4 Mineral filler. Mineral filler is the material which passes through 0.075 mm sieve size. The major components of the filler consist of rock dust, Portland cement, hydrated lime, ground limestone dust or fly ash. This makes the SMA mix stiffer and a rich binder. Breaching of the threshold level of the filler can lead to excessive stiffening of the mix, causing unfavorable conditions for compaction. This might lead to the cracking of the susceptible mix. In general, aggregates passing through 0.075 mm sieve size should be 8 to 12% of the total amount of aggregate in SMA mix. The main function of filler is to fill the voids in aggregate skeleton and make the mix denser by improving the cohesion of the asphalt binder and the stability too. In this study, a waste material called Bagu's dust is used as filler material in SMA mix. 1.5 Elastomer Modifier. The Elastomer Modifier consists of functional additive which is a smart solution to improve the properties of mix around the globe. It gives better durability, convincing anti-rutting characteristics, better aging resistance and enhanced performance. Apart from this, it is an alternative way to achieve a process of reliable modification of bituminous mix close to the same performance level with modified bitumen. In this study, commercially available elastomer modifier pellets are used. This product is a pelletized blend of cellulose fiber and functional additive. The composition consists of 20% and 80% by weight respectively. The quantity of elastomer modifier is added at a rate of 12% or 15%. In this study, dosage rate of 15% is considered for viscosity grade 30, which is recommended in the manual 20. The mixing of elastomer modifier with the mix is carried out by two modification procedures, i.e., dry process and wet process. In this research, the modification of the bitumen is carried out by adopting dry process technique. 1.6 Objectives of the work. To assess the performance of stone matrix asphalt mix with partial replacement of reclaimed asphalt pavement. To determine the feasibility of using reclaimed asphalt pavement in stone matrix asphalt mix. To determine the effect of elastomer modifier in stone matrix asphalt mix with reclaimed asphalt pavement. 1.6 Scope of the work. Recycling asphalt pavement initiates a cycle of 4R principles, where the materials can be recycled and reused, which leads to a sustainable use of natural resources. Reclaimed asphalt pavement is one such alternative to unexploited materials which can reduce the overuse of limited aggregates. By using reclaimed asphalt pavement, sustainability can be achieved without compromising its structural performance. As RAP is an aged material, to regain the fresh properties, different commercial rejuvenators are used. There are instances wherein commercial rejuvenators are not available. Therefore, this study analyzes the potential of modifying the asphalt with elastomer modifier as a substitute for commercial rejuvenators to increase the percentage of the reclaimed asphalt pavement materials which can meet the intensified needs more legitimately. 2 Laboratory investigations. 2.1 Aggregates. The aggregates were procured from different crushers. The basic tests were carried out on the aggregates, and it was found that aggregates procured from KMS crusher Bangalore, Karnataka were found to be within the required limits as per MORTH 16 for SMA mix. The basic test results are depicted in Table 1. Table 1 Tests on aggregates. Tests conducted. 2.2 Reclaimed asphalt pavement materials. The existing Bengaluru-Tirupati Highway, NH 206, from Karnataka Andhra Pradesh border to Chittoor is completely scarified, including subgrade and upgraded to cement concrete pavement. The scarified pavement sections were dumped at dumping sites. The pavement was 15 to 20 years old as per the records. The single-lane road was upgraded to 2 lanes undivided highway in the financial year 2000 to 2001. Hence, the old pavement was scarified. The physical tests on RAP aggregates are conducted and RAP binder is extracted by centrifuge extractor, and results are tabulated as shown in Table 2. 2.2 Bitumen. In the present study, viscosity grade, VG, 30 is used, which is obtained from Hinkle PVT Ltd, Mangalore. The tests on the bitumen is carried out as per IRCSP 73:2013, Guidelines for Paving Bitumen Specifications 19. The results are tabulated in the following Table 3. Table 3 Tests on bitumen. Tests conducted. Test results. Specifications. 2.3 Elastomer Modifier. In this research, a commercially available elastomer modifier is used, which is the combination of cellulose fiber and functional additive. It is a patent product obtained from Smart Technologies, Pune, Bengaluru. The characteristics of the modifier are shown in Table 4. Table 4 Characteristics of Elastomer Modifier. 2.4 Gradation of aggregates. After the basic tests, the aggregates are further used in the determination of the proper blend to give a good mix consisting of different aggregate sizes. The different sizes of aggregates used to obtain the proper blend are 20 mm downsize, 12 mm downsize, and 6 mm downsize and stone dust. 4,000 gm of aggregates were taken for sieve analysis. The aggregate gradation is carried out using the trial and error method, to determine the individual percentages of the different size aggregates to be used in the mix and should be within the limits as per MORTH Table 537-16. The sieve analysis results and obtained gradation of wearing course for conventional SMA mix is as shown in Table 5. 3 Results and discussions. 3.1 Marshall properties. The SMA mix design basically relies on volume trick properties such as air voids, voids in mineral aggregate, voids in the coarse aggregate and binder content. Another important consideration in designing SMA mix is the filler/additive. In this study, cellulose fiber was used as stabilizing additive and boguse dust was used as filler material. The Marshall specimen are cast and compacted with 50 blows on either side as per Marshall procedure. The SMA mix design shall meet the requirements 0 given in Table 6. The optimum binder content and optimum wrap content with and without elastomer modifier is obtained by casting Marshall specimens for different bitumen contents. 3 specimens are cast for each bitumen content. The Marshall test is carried out for 3 SMA mixes, i.e., conventional SMA mix with wrap without elastomer modifier and SMA mix with wrap and elastomer modifier. For conventional SMA mix, the Marshall specimens were cast for 5.75%, 6%, 6.25%, and 6.5% bitumen content and were tested. The optimum binder content was found to be 6%. The optimum wrap was determined by replacing wrap in different percentages, i.e., 10%, 20%, 30%, 40% and 50%. The bitumen was also varied in same range as in conventional SMA mix. The Marshall stability at 30% wrap replacement with 6% bitumen content was found to be highest when compared to other proportions. Hence, the optimum wrap was considered as 30%. An attempt is made to enhance the optimum wrap by adding elastomer modifier at a quantity of 15% of the weight of bitumen. This elastomer modified is added to the mix by dry process method. The bitumen content of 6% obtained for 30% wrap replacement was considered for further wrap replacement of 30%, 40%, 50%, 60%, 70%, and 80%. The Marshall properties at 60% wrap showed better results compared to other proportions. The Marshall results of all the mixes are tabulated in the Table 7. 3.2 Drain down test. The drain down characteristics for the SMA mix were conducted for the conventional SMA mix as well as for the SMA mix with optimized wrap with and without elastomer modifier. The results are tabulated in Table 8. Table 8 Drain down properties of SMA mixes. The drain down test results yielded good results. The drain down of bitumen of the specimens are found out to be well within the limit of 0.3% maximum as prescribed in MORTH 16. 3.3 Moisture susceptibility. The main factor leading to premature failure of the bituminous pavements is due to the presence of moisture in the pavement surface and the inability of aggregates to retain the coating in the presence of moisture. Hence, it is important to conduct tests regarding moisture susceptibility. Tensile strength ratio is carried out on the basis of the indirect tensile strength procedure. This test is done for the conventional SMA mix as well as for the SMA mix with optimized wrap with and without elastomer modifier. The number of blows for its is found out at 32 blows on both sides for conventional SMA mix, and for wrap replacement with and without elastomer modifier is found to be 28 and 25 blows each side respectively. The results for its and TS are for conventional SMA mix and SMA mix with optimized wrap with and without elastomer modifier are tabulated in Table 9. The results show that the SMA mix with optimized wrap with elastomer modifier is found to more moisture susceptibility than conventional SMA mix and optimized wrap without elastomer modifier. 3.4 Rutting characteristics. The rutting tests are conducted on the conventional SMA mix as well as for the SMA mix with optimized wrap with and without elastomer modifier. The test is carried out to find out the resistance to deformation due to repeated wheel load for wearing course. For this test, the maximum and minimum layer thickness is considered, which is 40 mm and 50 mm thick respectively, With tire pressure of 549 kPa, 5.6 kg per square centimeter, for each specimen at a frequency of 25 passes/min, and it is carried out at room temperature until 10,000 passes or 12 mm rut depth. The graphs of 40 mm and 50 mm thick specimens are shown in Figure 1 and Figure 2 respectively. The rutting test is conducted for conventional mix and optimized wrap with and without Elastomer Modifier. The thickness of test specimens is 40 mm and 50 mm. The result shows that for 40 mm thick beam the rut depth is 5.97, 4.59, and 3.73 mm respectively, and for 50 mm thick beam 4.48, 4.04 and 3.15 mm respectively for different mix. Hence by adding Elastomer Modifier it increases the wrap content to 60% and decreases rut depth. 3.5 Repeated Load Fatigue Test. The fatigue test is conducted on the conventional SMA mix and optimized wrap with and without the Elastomer Modifier. In this test Marshall specimens of 32, 28, and 25 blows respectively and tested in 4-point loading apparatus. The stress level and deformation are kept constant, which is 10% and 5 mm respectively. The test was carried out to find out the resistance to deformation due to repeated wheel load. The test results are shown in Figure 3. Figure 3. Fatigue results of different SMA mixes. From the results obtained it is observed that the failure criteria for 5 mm deformation at 10% stress level shows that 60% wrap with the addition of Elastomer Modifier in SMA mix increases the fatigue life cycles compared to conventional mix and optimum wrap without Elastomer Modifier. 4 Conclusions. The physical tests on virgin aggregates, reclaimed asphalt pavement, bogus dust, and bitumen, VG30, were carried out. Laboratory investigations on Marshall mix specimens of varying percentages of wrap replacement with and without modifier was done. Performance tests like drain drown, moisture susceptibility, rutting, and fatigue tests were conducted and the following conclusions were made. 1. The results obtained from basic laboratory tests of virgin aggregates, reclaimed asphalt pavement aggregates, bogus dust, and bitumen, VG30, are within the specified limit as prescribed by MORTH 500 to 35. 2. To determine the amount of wrap in the mix, Marshall properties are determined. At 30% wrap replacement, the stability value of the mix is found to be increased by 1.55 times than the conventional SMA mix. The obtained Marshall properties are within the specified limits as per MORTH. 3. By adding Elastomer Modifier, the optimum wrap is found to be 60% and Marshall properties are within the specified values as prescribed in MORTH. 4. The drain down test results yielded good results. The drain down of bitumen of the specimens was found out to be well within the limits, i.e., maximum of 0.3% as prescribed in MORTH. 5. The moisture susceptibility test results showed that SMA mix with 60% wrap with addition of Elastomer Modifier is found to be greater than the conventional SMA mix and SMA mix with 30% wrap without Elastomer Modifier. 6. The rutting test is conducted for conventional SMA mix and wrap materials with and without Elastomer Modifier. The results show that by adding Elastomer Modifier it increases the wrap content up to 60% and decreases rut depth, and hence it makes the mix rut resistant. 7. By conducting fatigue test for failure criteria of 5 mm deformation at 10% stress level shows that SMA mix with 60% wrap with addition of Elastomer Modifier increases the fatigue life cycles compared to conventional mix and wrap replacement without Elastomer Modifier. 8. The performance test results have yielded better results for SMA mix with 60% wrap replacement with Elastomer Modifier compared to conventional SMA mix and SMA mix with 30% wrap. Hence, Elastomer Modifier can be stated as an effective alternate to conventional SMA mix since it results in appropriate use of waste materials and enhancement in performance properties.